Remember, we're working with this formula. Force dotted with displacement vector, right? So I take my force and I dot it with, well, that's the unit tangent vector, and then I'm going to shorten it by how much? Just this little infinitesimal arc length, ds. And that would give me, right, this is a number. So this is some scalar multiple of t. So that it points in the direction of capital T, but it's been shortened to be infinitesimal. Does that make sense? It's like that calculates, this right here calculates the work done in this very, very small movement. It's how much work is done. And then what I want to do is continue to do that all the way around the path. And so I want to add all these up, right? And to add them up, you do an integral. That makes sense? I'm not going to do like a hard, rigorous proof. I mean, this is as much as I can do as a geometric idea here. This integral right here is a line integral over the curve C. So this is the thing you're moving along. And then what you're doing is basically adding up all the little dot products along the way. And that will give you the total work done by the field as you move through it on that path. So just keep in mind that when we're doing this formula, R of t is the vector function which draws C. So we need to know R of t. We need to be able to draw C. Capital T is the unit tangent vector. And do you all remember the formula for the unit tangent vector? It's the derivative of R of t divided by its own length. That's the formula, right? So it looks like this integral is going to kind of suck because somebody's going to give us a vector field. Remember I said someone will give you a vector field? We're going to take that vector field and dot it with this. And then do ds. Do you remember what ds was? Yeah, the square. This looks like it's going to be horrific, doesn't it? Y'all agree? It's not. Watch. Check this out. We have a lot of really good things that happen. Look, this capital T was this, right? And we said that ds was that square root of that junk, but that's really what the square root of that junk is, right? Yeah. So when you come in here and you go f dot t ds, t is this, ds is this, these cancel, right? And all you get is this. Now this is kind of hard to see, but what you're going to do is dot product those two things right there. And this just is kind of mind-blowing. What you're going to do is you're going to take your vector field and you're going to evaluate it along your curve. You're going to take that and dot it with the derivative of your curve. You take that dot product and you integrate that over C, which is going to be the A to B, which are your restrictions on T. So very nice formula at the end of the day. That's the one we want to remember. I think I summarize it right here. There it is. So we have a new notation. We have new notation. And what I mean by this new notation is like we've seen this. That's Cal 2. We've seen that. This is Cal 3. We've seen that. Cal 3. So this was Cal 2, you're integrating with respect to x. Cal 2, integrating with respect to x. Cal 3, this was a double integral, so we integrated with respect to area, right? Here we have a triple integral over a solid, so we integrated with respect to volume. When we started line integrals, we integrated with respect to s, right? And then we did x and y, and then we could do z also. But now this new notation, the line integral over c of f dotted dr, this is the new notation. This is the first time we've ever seen a vector in our differential, right? Like this has always been dx. X is a variable, right? Like x is a scalar. dA, a is a scalar. V is a scalar function, right? It doesn't have vectors involved. This is the first time we've ever had an integral where our differential we're putting a little r, a little vector symbol on the r. And that's because what is this now to us? Like this really is t dot ds. That's the definition of this. It's this is that, okay? So this is just a new notation for that. But we saw things canceled and it came out to this, right? And that's the one, here it is right here, okay? So the one that's boxed is the one that we want. Also note that when you change the direction of your path, that you do get a change in sign, all right? With vector, when you're doing line integrals over vector fields. That's highlighted because I may have had this in our notes and I may have changed it like here, but it might be something different in your notes. You don't have the notes online? It may not say quarter online, so I'm doing something a little different. Find the work done by the gradient vector field. Oh, cool. Find the work done. As soon as you see work, from now on, when you see work, you should be thinking this. FDR, all right? You should be thinking line integral over C of f dot dr. That's what you should be thinking when you think work now, all right? So we want to know the work done by the what? Because we're supposed to have a vector field given to us, right? To do this, I need a vector field and I need a path. Do we have a path? Yes. Yes, the top quarter of the unit circle in the counterclockwise direction. So I guess first quadrant, okay? But see, I need a field. I need a vector field in order to calculate work. Do I have a vector field? Yeah. Is it given directly to me? I have to find it because I'm not given f. I'm told that the f that I need to use here is the gradient vector field of that scalar function, and we did that a couple of days ago. Remember, if someone gives you a scalar function, what's the gradient vector field of a scalar function? The partials. So there's kind of a hidden, instead of me just coming and giving this problem saying, hey, here's the vector field, here's the path, go find the work, I'm actually hiding the vector field in the wording here. So first thing I'm going to do is calculate f. I need to figure out what this is. And it's the gradient vector field of the scalar function f. Why do I know that? Because it told me. It said find the work done by the gradient vector field of that. So what is the gradient vector field of that? Well, it's the partial of little f with respect to x, partial of little f with respect to y. It's two-dimensional, right? Two-dimensional vector field. And what is it?
2x plus and then 2y. Oh wait, no. 2x plus 2.
Maybe we should just expand that up there. What would that be?
X squared plus y squared plus 2xy.
Okay, yep. Do it that way, that's fine. Okay, so that's, shit. Oh, wow, that didn't spill. That's this thing expanded, right? So take the partial of that with respect to x, and you get 2x plus?
Should be 2y plus
2y plus 2x.
Same thing for the other one.
Same thing for the other one. Doesn't matter what order I put those in, right? So that's your gradient vector field. So this is a vector field, right? It is a vector field. But it happens to be a gradient vector field because it is the gradient of a scalar function. So we would like to know the work done by this field, all right, on the path as an object moves along this path, traversing the top quarter of the unit circle in the counterclockwise direction. So now let's get our path. So notice I'm not, this is C, right? This is C. This is my path. Is that a question or comment?
Interpretation of top quarter.
I said let's do first quadrant.
Okay.
Because you could argue just as well to do the other side, couldn't you?
I was thinking the top 45, like 40, from 45 degrees to.
Oh, okay. You could look at, yeah. So just for clarity, let's just say, first octant or first quadrant. Sorry, we're in two dimensions. Yeah. So 0 to pi over 2, if you like. Okay. Yeah, I changed it because originally this said I think the top half of the unit circle. I just came real quick and put top quarter in the middle of another class. So, all right, there's what we're talking about, right? So remember, we're supposed to compute this, right? We're supposed to compute this. Now, what is this? Let's write this down in the form that I had boxed up. It was integral from A to B, right? It was f evaluated where? Where do we evaluate the vector field?
The vector.
On the vector curve, okay, on the vector function, r of t. And then we dot that with what? R prime of t. And this will be with respect to t. So there's our big formula for calculating work. I told you this is the big formula, but this is the notation for it. This is what we really have to do, all right? So now, r prime of t, we need r of t. We never wrote down r of t, sorry. We never wrote down what r of t is. I drew it, but what is it? So what is r of t? So I'm going to write it in vector form. So what is it? Cosine t, sine t. We've been beating this thing to death, haven't we? T is between 0 and pi over 2, because we're only doing the top quarter, right hand, quarter, first octant, first quadrant, whatever, yes? All right, so doesn't this give us our restrictions, right, A and B? It gives us that. We need the derivative. Let's get the derivative of this. Derivative of this is actually not bad. Negative sine t, cosine t. Are we ready to put everything? Yes.
When you wrote down the formula on the right, you used big F the vector field. Am I? Should that have been little f, or am I confused?
Little f is a scalar function, and we created the gradient vector field from it.
Oh, okay. I see now.
Yeah, I think, going back and thinking about this more, this being the first example, I should have just given us this vector field.
Okay.
I should just say, hey, let's start the problem by just doing this. Adding that other part in there just kind of, I think, is confusing people more than anything else. So can we just imagine that this isn't here? And I just started the problem out by defining our vector field to be that. Okay? It's like, here's a vector field. Find the work done on the path traversing this thing. All right? So we now need to just plug everything into this, right? This part is the part that I think is most confusing. What does it mean to take your vector field and evaluate it on the vector curve? Take the x and y component, x and y components of the vector field, of the path. This is our x, this is our y, and just take them and replace x and y with those things. All right? It's weird, like I showed you, this was the part I put in red. Like, it's weird notation, but it's not difficult to do the computation, or the plugging in. So I think I'll do it over here. So here's where we are. That right there, which is really this, is equal to integral from 0 to pi over 2. And now we have a vector, okay? This is a vector. When we plug r of t into this vector field, it is a vector. So we're taking this, replacing x with cosine t, y with sine t. So we have 2 cosine t, comma 2 sine t, plus 2 sine t, comma, so that's the first component, and then the second component is exactly the same, isn't it? So 2 sine t plus 2 cosine t. Close the vector. I am done with this part. That is this, right? Then I want to dot that with the derivative of r. So that's this, right? Negative sine t, cosine t, and then dt. And what's the great thing about dot products? When you take the dot product of two vectors, you get a what?
Another vector. A scalar.
A scalar, right, exactly. So we're going to be trying to integrate something in a second. It's going to be a scalar function. The vectors are going to go away, aren't they?
Yeah.
That's a great thing. So let's do that now. Integral 0 to pi over 2. And remember how to dot, right? You do the first component here times the first component here. So what's that when you multiply that through? So the sign has to go to each of those. So negative 2 sine t cosine t. It's the first part, right? Negative sine t times that. And then here, negative 2 sine squared t. Right? So that's our first multiplication. Then what? Dot product, so plus. And now we do this piece times that piece. And again, distribute the cosine through. So, ooh, look at that. 2 sine t cosine t. And then, what do we have? Plus 2 cosine squared t. Right? We're good, right? Okay, so these happen to cancel.
You can pull out the sine square, cosine square.
Do what?
If you pull out the sine square and the cosine.
One of them's negative, one of them's positive. That's why I was kind of slowing down. I was really hoping that that was going to turn into like the Pythagorean identity, but it doesn't.
Well, one was a double angle, right? Well, you could turn the 2 sine squared to double, like or it's like one of those half double angles.
Yes, we could. Let me clean up. Let me pull a 2 out. Can I pull a 2 out? 2 integral 0 to pi over 2. And then let me change the order. Cosine squared t minus sine squared t. Right? dt. That is an identity, right? Yeah, or it's pretty close. Where's your, let me see yours. You got yours right here. Referring to your, yep, there we go. Where is it on here? Right there. The double angle formulas.
Oh, you could do, you could turn the sine squared t into 1 plus or 1 minus.
Yes.
Is that what you're going to?
No, I'm not going to do that. You could do that. This is, there's a simpler formula. This is just cosine 2t.
Oh yeah.
That's just cosine 2t. Right? So if you look on your pre-cal formulas, this is one of your double angle identities. The one that most people are familiar with was this one. Sine of 2x is 2 sine x cosine x. That's a very common double angle identity that most people know, but what is cosine of 2x? There's 3 equivalent formulas for it, and this is one of them. So that one becomes that, and that's going to be much easier to integrate, isn't it?
Yep.
So this will become integral 0 to pi over 2, and we're going to be integrating cosine 2t dt, and the antiderivative of that, yeah, 1/2 sine 2t, and we had a 2 on the outside, which means it's just going to be sine 2t, and we're going to be integrating that from 0 to pi over 2. And when you plug pi over 2 in, you get sine of pi, which is 0, right? Because pi over 2 goes in here, and you get 0. When you plug in 0, you get 0, so you get 0. So you get 0 work. Pretty boring. You could make it a little more interesting by maybe doing not like the top quarter, but you could do maybe like this part right? Maybe where that's like pi over 4 instead. Because you would have work here. Because then it would go from 0 to pi over 4. And when you plug pi over 4 in here, you get sine of pi over 2, which would be 1. So your work would be 1 instead of what we're getting. Does that make sense?
Clockwise instead of counterclockwise, say that we do it clockwise, would that also be 0?
It should be 0 because remember, changing the direction of the path is going to change the sign, so it would be -0, which is still 0. Okay, does this make sense as far as what I did? All right. We have 20 minutes left. Let's take a look at this one. I'm sorry? Did I watch what?
Game of Thrones.
No, I've seen on TV that the premiere came out, I guess, for their last season. Yeah. I don't watch it, so I've been told I need to watch it. My Cal once told me the same thing. Is it on Netflix or anything?
It's on HBO.
HBO. Yeah. Okay. Maybe one of these days I'll get. I'll just do it like I did with Breaking Bad. I'll just like do it all in like 2 weeks. I'll watch the entire all seasons. You know. Yeah. I'll just wait and then just. Okay. Yeah. Find FDR, where F is this vector field. So I'm giving you the vector field explicitly, right? Here it is. It's not like the previous problem where we had to calculate the vector field. It's there. It's not pretty. Does anyone recognize that vector field?
Isn't that the unit?
Yeah, this is, remember the gravitation one where everything was going in like that? This is a two-dimensional version, but you look like you want to say something. It's not going in. It's going out. Yeah, because on the one with gravitation, we had negative and negative, and then there was a z component doing the same thing. So everything was trying to go opposite direction. Here, everything is going out. So this is like, I don't know, the sun, yeah, heat going out or something. All right, whatever. Okay, so we've got this vector field, right? And then we're trying to move this thing through that vector field, and we want to know the work done by trying to move this thing through this field. All right. So if this is truly like a magnetic field, think about it this way. If this is truly like some magnetic field pushing everything away like this, everything is outward like this, and I try and come in here on this parabola, which is 1 plus x squared. So I come in here and I try and move from here to here. Like I'm trying to go from here, moving through here, right? Like this. So when I'm moving down like this, I'm moving against the field, aren't I? Yeah. And then when I come back this way, I'm going with the field. We might get 0 again here. The symmetry seems like we might get 0, doesn't it?
It does.
So let's do this. Let's just go from here to 0, 0, because I don't want to get 0 as an answer again. Do y'all see with the symmetry it looks like that would do that? Okay. All right, so let's crank this out. I need to know what R of t is. I need to know my path. So my path is a vector function. It's two-dimensional. How are you going to draw this path? You got to use t's. So what's your x component function going to be? Just t. Okay, and what's your y component function going to be? 1 plus t squared. So this is exactly what we did earlier, but now we're putting it in a vector function instead of individual parametric equations. And what is my t going to vary from?
1 to 1.
Yeah, so t is my x, so I want to go from -1, and I changed it to 0. Is that okay? So -1 to 0. We good? All right, I'm going to need the derivative of this. One, 2t. Right, there's my derivative. And then I'm going to need to plug that vector function into my vector field. So do you feel like we're ready to start putting everything in? Start creating the integral here? Okay, so integral over c of f dot dr should be the integral from a to b, which is -1 to 0, of f evaluated at r of t. So what is my vector field evaluated at r of t? So what does this become? X becomes t over square root of, I need more room, t over square root of, what'd you say? T squared plus 1 plus t squared squared, right? Comma, now y, 1 plus t squared over square root of, well, the same thing, isn't it? T squared plus 1 plus t squared squared. Crap, I'm going to run out of room. Dot that with what?
The
Derivative 1, 2t dt. I'm off camera, but who cares? All right, this will be equal to integral from -1 to 0, dot product time. So when we dot these, first component's 1 times that, it's just that, right? That's good to see. Don't have to do anything crazy there. Plus, now this dotted with 2t, right? Or this multiplied times 2t. 2t plus 2t cubed over the same thing down here. And there's no more vector, right? We have the same denominator, don't we? Those are the same denominators, so I can put those together all into one. Any questions on how I got to this? Let's see if we can take this one all the way, because I don't think I'll be able to do another example. Let's see, -1 to 0. My numerator is 2t cubed plus 3t, right? So I can put this t and that t together, 2t together, so 3t over the square root of, now this doesn't look good. If we were to square that right there, we get t to the 4th plus 2t squared, right? Right, this. We get, well, I'll do it in the order it appears. 1 plus t squared plus t squared plus t to the 4th. So t to the 4th plus 2t plus 1. But what's down here with it?
T squared.
T squared. So this is really going to become t to the 4th plus 3t squared plus 1, right? dt? Yay or nay?
Yeah.
Yay.
Okay. And was this problem specially made for us? Can you tell that this problem was very specially made? Were you saying something? What were you saying? No, I thought I heard you say it. What did you say? You sub? What's u? T to the 4th. Are we going to get that lucky? Are we going to get that lucky? We're not getting lucky. They made it this way. Let's see if it works. The derivative of this is 4t cubed plus 6t, and that's it, right? dt? And isn't that almost what we have on top?
Oh, it's just.
We're just off by 2. Yeah, so they made this for us, right? This is a gift from the author, I guess. But in the real world, right, this would be a point at which you would crank it into a computer, you know, if it was something you couldn't do. But we can go half du is equal to 2t cubed plus 3t dt. And so this is the part that always bothers me, because I know everyone learns this part differently, like u substitution and all that. I mean, I've always taught my students to try and look at what you have here and see if you can create it from this. So just dividing both sides by 2. This right here matches exactly with that. So everything I circled in blue gets replaced with 1/2 du. I know other students are taught to take this, solve for dt, and then plug that in, then cancel things out. It works both ways. It doesn't matter how you do it. All right, so this integral now becomes, now watch what I'm going to do. I'm going to now do an indefinite integral over here. Okay, so I'm not going to go -1 to 0 right now. I'm just going to do an indefinite integral. And I get 1/2 du. So I'm making this is being replaced with that. And then over 1 over root u, right, is what would be here. So I'm going to write that u to the -1/2. That's 1 over root u. And now I do my power rule. So 1/2 times antiderivative of that is 2 roots of u, plus some constant of integration if it's indefinite, right? So just check it here. This would come out. Yeah, that should work, right? So this is really just square root of u plus a constant. And u was all that crap up there, right? So now I'm going to come back to this. Now what I say is this is the antiderivative of that, which I just found was the square root of this, but evaluated from -1 to 0. So what happens when you plug in -1? I'm sorry, when you plug in 0, you just get root 1, right? And then minus, let's see, root -1 in there, you're going to get 1 plus 3.
Wouldn't it be 0 minus the...
0.
Wait, wouldn't it stay as a negative though?
Where?
Wait, on the...
You plug 0 in first, right? 0 goes in first, and that gives you just root 1. When you plug -1 in here, you get 1 plus, and then you get 1 there again, so 3 plus 1, that's 5, so root 5. 1 minus root 5. Whatever that is. It's negative, I can tell you that. And what would have happened, just out of curiosity, what would have happened had we gone from -1 to 1? Like, what if we had actually done this problem? The only thing that changed would be this, right? So when we plug 1 in here, we're going to get root 5. When we plug -1 in here, we're going to get root 5. So they're going to cancel. So we would have had 0. Okay, what do you think?
So the vector field doesn't alter the shape of our path, it just alters like our speed?
No. Think of it this way. Like a magnetic field, and let's say we're trying to force some metal ball through the path. That magnetic field is going to try and resist our motion, right? Because the field was going away. The field is going out like this, but we were trying to move, we stopped it here. So we were trying to go from here, right? But we're going against the field, so there's a resistance. So it's not knocking us off our path. We are fixed on that path. We are going to make it from that point to that point. The question is how much work is done in getting there. Okay? Does that answer your question? Okay. Okay, so we only have a few minutes, but this is good to kind of end with some of the notation. You know how we were doing, before this, we were doing line integrals with respect to x, y, and z, before we brought the vector stuff into it, and I said we'd use it later? This is a connection between the two. So suppose that you are given a vector field, three-dimensional vector field, where you have what we will call P, Q, and R. So you have three component functions, P, Q, and R. Then the line integral of the vector field along C, which is this, FDR, this calculates the work. This is equal to, check this out, these are line integrals without any vector stuff in here. So it's, you take the P1 over C with respect to x, you add to it the Q function over C with respect to y, and then the R function with respect to z. Okay, so this is the connection between those line integrals with respect to x, y, and z and the original work integral. We can use this. We will use it later. More formulas for you to have, right? Five minutes. Is this our last example? No. Maybe we can set this one up. I know you want to go, I do too, but we just don't have time to waste. A 180-pound man is carrying a 20-pound tool bag, walks up a helical staircase wrapped around a 20-foot radius cylindrical silo. If it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? Work is measured in foot-pounds. Also, weight is a force. So,
Would your equation would be like the cosine t, sine of t, and then your z would just be like z, so that way it's creating like a spiral going up.
yeah, you know what? Do I have a picture? Yeah, I do. Here we go. Man walking. So he's going up a helical staircase wrapped around a cylindrical silo with a 20-foot radius, and the silo is 90 feet tall. So you saw that picture there. So this is 90 feet, right? This is 20 feet. And we want to know how much work is done to get him from the bottom to the top, right? Going around the staircase. So let's imagine he starts here, he goes around. I think I got that pretty close, whatever. It was 3 complete revolutions to get him to the top, right? So this is a work problem, which means we need a vector field. We need a field that represents the force. So what is the only force acting on this man walking up the silo? Gravity. So our vector field looks like this. It's just straight down vectors, right? And what would I use for gravity?
Mass times gravitational constant.
Okay, so do we know the force acting on the man as he is trying to go up? Do we know it?
You can use the x, negative y over the x squared.
That would be going to the center of the Earth. We're imagining this is just flat and it's a straight down force.
-1, -1.
What's a vector going straight down?
0, -1.
0? It's 3-dimensional,
Oh.
right?
0, negative.
0, 0, and then straight down, right? How much force? It's his weight. How much does he weigh?
180.
But he's carrying a 20-pound tool bag. 200, okay? And we're going to look at it as negative 200. That means it's down. That's our field, yes? Go ahead.
This class weight was, oh, never mind. I see now.
Sure? Yeah, mass times force, yes, but we don't need that because weight is mass times force, right? I mean, mass times the gravitational, right, is your weight,
Yes. We're given weight.
right?
Mass. Correct?
That's right.
Okay.
We're given his weight, not his mass. Was there another?
I see now, because I was thinking you have to multiply by 9.8, but like weight is like.
Yeah, that's right. It already accounts for the force of gravity. Okay, so now, look, this is our force down, right? This is weight. So now what? We have the field. What now? We need the path. We need his path, right? And his path, how do we draw this path? You were onto it.
Like cosine t, sine t.
It's cosine t, sine t, but there's a little catch because it's not a unit circle.
Z?
Oh, 20.
It's 20 cosine t, 20 sine t. That'll give us a radius of,
And then just t.
and then is it just t? It could be t, but we want to be able to go around, we want to get all the way up to 90 in 3 rotations.
So 30.
30t?
Would that do it?
Wait, why 30t?
Because we need to go from 0 to 3 in order to do 3 revolutions of 20 cos t and 20 sin t.
Here's the way that I kind of visualize this. You know what? Why don't we, it's 240. This is a good, why don't you think about what needs to be here? All right? Why don't you think about what needs to be in here for this and what your restrictions on t are? Like, what are the restrictions on t, and then what would this be so that he can get up to the top of this silo, which is 90 feet high, in 3 complete revolutions? Okay, so there are probably different ways you can do it. Just depends on what you do with this. And but here's the cool thing I think about this problem. Those of you who have taken physics know that there's a shortcut answer to this. Maybe you know that, because we're going to do this vector function where you, and then what are we going to plug into the vector function? The path, right? But this doesn't have any variables in it, right? So we're really just going to wind up dotting this with the derivative of that, right? And when I dot, imagine what the derivative of this would look like. Negative 20 sine t, 20 cosine t, and then whatever that is, its derivative, right? Okay, so that part right there, when we dot this, it's 0 times that first part's gone. 0 times second part's gone. It's only this times this, which in physics you should know this, that when it comes to moving an object from the ground up, this direction requires no work. It's only the up and down that matters. So him wrapping around this thing has no impact on his work. What matters is just how far he goes from here to here. That's the part that matters. His vertical displacement is the only thing that's going to contribute to the work. And you can see it from here. But that's next class, okay? We'll pick up from there. Y'all have a good one. I do have the take-homes from last time and the other ones. So I can hand those back. Let me turn my camera off.